today's physics is it was known that current produces a magnetic field, and this fact came as a surprise to the scientist who discovered this fact. Perhaps even more surprising was the discovery of the reverse effect. A magnetic field can produce an electric field that can drive a current. This link between the magnetic field and electric field it induces is now called Faraday Law of Induction. The observation of Faraday and other scientists that led to this law were at just basic science. Today, however, application of that effect is almost everywhere. For example, electric guitar, electric generator, graphic tablets, transformer, wireless energy transfer, and many more. So today we will see how this change in magnetic field produce the electric field that induces the current or that drives the current in our laboratory.
In Faraday's first experiment, we have a conducting loop connected to a sensitive galvanometer. Because there is no battery or no other source of EMF included, there is no current in the circuit. However, if we move a bar magnet toward the loop, a current suddenly appears in the circuit. The current disappears when the magnet stops. If we then move the magnet away, a current again suddenly appears, but now in the opposite direction. From the experiment, we have the following conclusions. A current appears only if there is relative motion between the loop and the magnet. That is, one must move relative to the other. The current disappears when the relative motion between them ceases. Second important point is faster motion produces a greater current. And finally, if moving the magnet north pole toward the loop causes, say, clockwise current, then moving the north pole away causes anti-clockwise current. Moving the south pole toward or away from the loop also causes current, but in the reverse direction. The current produced in the loop is called an induced current. The work done per unit charge to produce that current is called an induced EMF, and the process of producing the current and the EMF is called induction. Faraday realized that an EMF and current can be induced in a loop by changing the amount of magnetic field passing through the loop. He further realized that the amount of magnetic field can be visualized in terms of the magnetic field lines passing through the loop. Faraday law of induction states that an EMF is induced in the loop when the number of magnetic field lines that pass through the loop is changing. The actual number of field lines passing through the loop does not matter. The value of induced EMF and induced current are determined by the rate at which that number changes. In this experiment, the magnetic field lines spread out from the north pole of the magnet. Thus, as we move the north pole closer to the loop, the number of field lines passing through the loop increases. That increase apparently causes conduction electron in the loop to move and provides energy in their motion. When the magnet stops moving, the number of field lines through the loop no longer changes, and induced current and induced EMF disappears. In Faraday's second experiment, when the switch is open, there is no field line. When we turn on the current in the right hand loop, the increasing current builds up a magnetic field around that loop and at the left hand loop. While the field builds, the number of magnetic field lines through the left hand loop increases. As in the first experiment, the increase in field line through that loop apparently induces a current and an EMF there. When the current in the right hand loop reaches a final steady value, The number of field lines through the left hand loop no longer changes and induced current and induced EMF disappears. Now we had applied a AC supply to the primary loop or the left hand loop, then there is deflection on the galvanometer due to induced EMF in the right hand loop. This is due to the magnetic field lines produced in the primary loop or the left hand loop. As we change the frequency of AC, then the deflection on the galvanometer changes frequently. Now as I stop the AC supply, then there is no deflection, but when we switch on, then there is deflection on the galvanometer. Now you can see a pure sine wave is applied to the on the left hand loop, then there is a clear sine wave like signal on the galvanometer in the right hand loop due to induced EMF. If we change this sine wave to a square wave, then the deflection on the galvanometer is like a square. Now I switch on the DC supply, and while switch on or off DC supply, if I inserted iron rod, then you can see the deflection on the galvanometer increases, and if I remove, then deflection on galvanometer decreases. So this change in deflection of galvanometer can be clearly seen. Now again in the AC supply, I am inserting the iron rod, then you can see there is a significant change in the deflection of the galvanometer. So let us see with the help of cathode ray oscilloscope CRO how the input applied and output applied changes. Now we had applied the input and output to the CRO, which are applied to the primary and secondary coil. Now you can see that this is the input supply to the primary coil. You can see it is a pure sine wave, and this is the output. You can see that there is a phase change between the input and output. The phase change is clearly 180 degree between the input and the output. So in the final we have the definition of Faraday law in a useful manner is that the magnitude of the EMF induced in a conducting loop is equal to the rate at which the magnetic flux through that loop changes with time.